Hello everyone, welcome to our channel. So in this series we are completing the gate control system questions. So here we are taking one more question. This question related to state space analysis. So I'm stating the question. So consider a state system governed by the following equation x1 t by dt. This thing we can also write x1 dot. Okay. They given the x2 minus x1. So here x1 x2 is a state. Okay. And dx2 by dt, this we can also write the x2 dot equal to x1 minus x2. Initial condition are such that x1 0 less than to x2 0 less than infinity. Alright. So this is also finite. Okay. Some value will be there, but actually less than the infinity. Alright, so let x1f equal to limit t tends to infinity x1 t, and they are asking this one value. This is a final state value they are asking, and for this, which option is correct? So as we know, here, x1 x dot is equal to, you can see x dot is equal to ax. Okay, like that equation is given. So this is like a homogeneous system. For this, what's the solution for this? Xt is equal to e the power 80 into x0. This is our initial value. Basically they are asking the zero input response. Okay, all right. So here for this, how to solve this question and what's of essential useful data to be required for this. So one more thing actually here, e the power 80, this is our state transition matrix 5t. So once we find out this value, we can find out the put the limit t tends to infinity, we can find out the our final value, final state value. Okay, so let's just start. What's the essential useful data is required for this. So here you can see 0 input responsibility system x dot is equal to xt is given by, they given like that. Okay, xt is equal to e the power 80 into x dot. So where xt is a state vector. All right, and a is our state transition state matrix. A is a state matrix, but e the power 80 is our state transition matrix. Okay, and x dot is our initial state vector. So here is a x1 and x2. x1 0, we can say x2 0. This is complete, we are saying here x dot. Okay, and state transition matrix given by that e the power 80 equal to fit. We can also, this is Laplace inverse of si minus a inverse. All right, so let me write down the state space equation. So x dot equal to x1 dot. Okay, and x2 dot is equal to, we can say here also like that, no need to write that much. You can say x1 dot is equal to d2 by dx1 dot. So here like how to write down x1 dot and x2 dot. This is state velocity vector, we can say x dot. All right, this is a matrix we need to find out, a state matrix. This is x1 and x2. All right, So x1, first we should be x1 value, x1 coefficient. So where is the x1 coefficient here? For this dx1 or dx1 dot, so here is a -1. So don't make a mistake here. Okay, they put the write the x1 in the like first they write the x2 then x1. We want to x1 first, so -1 and +1. So if any confusion, you can write also this one minus x1 plus x2. Okay, this is okay, this is all right, this sequence is good. Okay, and we should be clear about this. It's bluntly like sometimes 1 minus 1, so this is a comment mistake actually. Okay, so minus x1 plus x2. So here this is a -1 plus 1 minus plus 1 minus 1. All right, this is my A matrix. So our agenda, we need to find out the S minus A inverse Laplace inverse. We need to find out the phi t here. So Si minus A equal to, this is a I is a identity matrix. So here we are taking 2 by 2 matrix, identity matrix. So yes, 0 0, yes, all right. And minus sorry, A matrix is -1 plus 1 minus 1. So how much is coming? Let me solve it. So this is a S plus 1, all right. And this is -1, this is also -1, this is S plus 1. Okay, hope you understood. And finally we need to do the Laplace inverse, sorry, matrix inverse here. This is matrix, all right. So how to do that? I recommend that here for 2 by 2 matrix inverse, you should remember like this is 2 by 2 matrix A, B, C, D. Okay, so what is the inverse of A inverse? Determinant. So D, A minus B minus C. So main diagonal element going to interchange, and BC just put the minus, this minus B minus C, all right. And here the determinant A is equal to AD minus BC, and it should be greater than 0. It should not equal to 0. Not equal to 0 means if it's 0 then it not exist, right? Okay, so the same thing we have to apply here. So here this is determinant for this uh, determinant for this okay. So here is a s plus 1 whole square minus 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 1. Okay, minus plus 1 and again minus coming, and since this main element is same, so there is no impact if you interchange also, and this is plus 1 and plus 1. All right. So we can solve more further also. Let me simplify further. So s square minus 1, we can also write s plus 1. All right, so this will be I'm applying this formula. Simple. All right, hope you understood. So and then what's coming, this one actually Si minus A inverse is coming S plus 1 1 1 1, and it is coming S plus 2 into S. All right, here also S plus 1. Okay, then finally we need to do Laplace inverse. So each element is we can say each term we need to do a Laplace inverse. Okay, so let me Laplace inverse of the s plus 1 by 1. Yes, I am entering this multiplying inside this term, and this is a s plus 1. Okay, so how to do that? Like, let me take one term. This transfer function we can say actually, but okay, this is a Laplace domain. So s plus 1 by s plus 2, we need to do the partial fraction. So s plus v by s plus 2. Okay, so how to solve it? As plus 1 is equal to, and here we can find out the h equal to, otherwise just solve it first, collect the same term s plus b and plus 2a, and then compare it for equivalent term. So so a plus b equal to 1, and 2a equal, this is constant term, is a 1. Okay, so here we get the b equal to 1 by 2 and a is a 1 by 2. Yes, put the a here, we get the final b here. Alright, so b 1 by 2, a 1 by 2, and for this, like, we can straight away we can also find out a is equal to s plus 1, like s 0 now, so base put the s plus remaining term and s equal to 0. Similarly b s plus 2 here, so s plus 2 is equal to 0, then s equal to minus 2, so s plus 1 by s, and we are putting the s equal to minus 2. Okay, so what's the value coming for this coming here 0 1 by 2. All right, and here is a here we coming 0 minus 2, so it's coming minus 1 minus 2 is coming plus 1 by 2. All right, so yesterday we can also find out. So for so this is this term is same, right? This term, so for this term and this term we find out the Laplace inverse. So finally we can say Laplace inverse of this term 1 by s, so 1 by 2 by s plus 1 by 2 plus s plus 2, and Laplace inverse for this final will get the 1 by 2 plus e to the power minus 2t and ut, because the ROC will be in a right hand side of this plane. Okay, so all right, so here 1 by 2 e to the power minus 2t. Similarly for this term we can also find out similarly. So here let me write this term 1 by s plus 2, so a by s plus b by s 2. So what is the a here? A value we are finding the 1 by s plus 2, s is equal to 0, so it's coming 1 by 2. So b is equal to 1 by s equal to minus 2, so coming minus 1 by 2. Okay, so this term is, so what is the Laplace inverse for this term? Is coming 1 by 2. Here is a, we missing one more term, right? Here is a 1 by 2. All right, don't commit mistake. Okay, so 1 by 2 minus 1 by 2 . Okay, so here ultimately we find out the finite state transition matrix. So here is a 1 by 2 plus 1 by 2 e the power e the power minus 2t ut. This is a term. Okay, and this is a same. And here is a all right. So here so we need to find out the final state, right? So we can say x t tends to infinity. We can also say based on the given question, let me change it also. Here we can also say x1f. Yeah, let me take more clear. So x ft. Okay, so just we are taking here two state. So this will be limit t tends to infinity, and this is a e the power at and into initial condition, right? Like that. Okay, so this depends our state transformation will depend upon the t wave function, so we need to apply here only. Okay, so here what is the exponential term? It goes to 0 once t tends to infinity. Okay, so finally we get here x1 f t. So here get the 1 by 2 1 by 2 1 by 2 1 by 2 when we t tends to infinity. All right, and this is a coming x1 0 x2 0. This is initial condition, right? So finally x1 ft is coming 1 by 2 x1 0. Okay, similarly x2 f is how much? Same thing, right? So basically x1 ft and x2 ft is equal, and but it's less than the infinity finite state. Some value will be there. Okay, so like that we can solve it. So here x1 and x2 is not initial condition not given numerically actually. So if you given numerical, we can find the numerically also. Okay, like they given here x1 0 less than the x2 less than to infinity, right? This condition they given actually. So x1 generally 1 and 2, but always time it should be always same actually here value. Okay, so we find out this answer. So for this what's the option would correct? So here's option will be C is correct. Okay, and one more thing actually, like here what approach we approach is standard way, like we need to find out the state transition matrix. Okay, and then finally we find out the were in individual state final value. So here we one more thing actually, like final value theorem, if you apply here, like we know final value theorem here, like like st, like any system, yeah, any input ct, any function, so t tends to infinity. Okay, and we can say here c infinity. So here if you convert in a s in a final value theorem, so usually s into capital S. Actually my point is that rather than finding this this Laplace inverse, actually straight away we can find out here. How? Let me see here. Like si minus a inverse we find out already na, this one. Let me write here. Uh, Here we can say xt. Okay, so what we are doing here, e the power at and xt. All right, we are doing like that. This is a initial condition, but we can also say like that uh, and one more thing, actually here if you um, light in correct way, like t tends to infinity, and we are doing here e the power at in x0. Here we can say also like s0 as si minus a inverse. Okay, into x0. So what is a si minus a inverse? Already we find out s plus 2. Here is a s plus 1 and 1 s plus 1. All right, so we put then s is cancel out, right? S term cancel out, so we get the s plus 2. Then here we can apply the 0 s, put the 0, you will get the 1 by 2, 1 1 1 1. This is a 1, yeah, 0 na, s tends 0. So again you will get the same value, 1 by 2, 1 by 2, 1 by 2 and 1 by 2. So again if you apply a condition, same thing you will get the. So here we can also write here, this is a final value, final state. So x1 xf, we can write xft, and again if you like that. Okay, so this will be coming here x1 0, x2 0. So my point is that no need to do the Laplace inverse like partial fraction and all. Straight away we can apply the final value. Okay, other thing is same like 1 by 2. Okay, so like that, but we need to ensure how to apply the final value theorem. Okay, so that's all. Hope you understood. And first we apply the standard way, and then final we, rather than go for a standard way, we can apply the final value theorem. No need to convert in Laplace in the time domain. Okay, so that's all for this video. Okay, hope you understood. If any doubt, please do comments, and that's all. Thanks a lot.